Alright guys, welcome back to another lecture. In today's lecture we're going to be talking about periodic trends. So when we talk about periodic trends, we see that the periodic table is arranged into columns and rows, and the atoms within each column usually have very similar traits to one another. So if you took a look and you look at the alkali metals, we have lithium and sodium and potassium, and as I go down, we'll find out that each of these alkali earth metals, or any column or group that's going down, are going to have pretty similar properties to one another, and we refer to these as periodic trends when we're going along the periodic table. So we're going to examine several of these traits in this chapter, the first of which will be effective nuclear charge. Then we're going to look at atomic radii. We'll go to ionization energy, which is how much energy is required to remove an electron from an atom. And then finally we will finish up with the electron affinity, which is how strong or how much affinity there is to attract an electron to an atom. So how strong that affinity is. So these are very important trends and concepts to understand because they can help predict atom behavior and bonding patterns down the road when we start taking a look at why certain bonds form and why other bonds would not form. So let's go ahead and get started. We're going to break this up into two lectures. So we will cover effective nuclear charge and atomic radii in this lecture, and in the next lecture we'll talk about the ionization energy and the electron affinity. So if we look here, let's start by talking about effective nuclear charge. So what is effective nuclear charge? We know that electrons occupy shells that are around a nucleus, and those electrons are held in place within their shells by the attractive force of the protons. Electrons all have a negative charge, so they would initially want to repulse one another and get as far away as possible. It's the protons that are keeping them in place and sort of creating that force that draws them in towards the nucleus and keeps them where they need to be. So we know that electrons are held in place by the attractive forces of the protons, and how tightly bound these valence electrons are. Now keep in mind, valence electrons are only the electrons that are found in the outermost shell, and when we talk about outermost shell we're talking about quantum levels, so n equals 2, n equals 3, etc. We're talking about how tightly bound these valence electrons we find are to the nucleus, and that's the strength of attraction between those two. That's referred to as the effective nuclear charge. So if you take a look, I'm going to draw the nucleus down here, and I'm going to put a positive charge in it. Now we're going to have a varying amount of protons depending on which atom we're talking about, but for right now let's just use a general plus here, and I'll draw a electron shell around here. And the electron shell, the first shell is 1s, and that can hold 2 electrons. And so when we're talking about effective nuclear charge, we're talking about how well these electrons are bound to the nucleus. Now the 1s shell is going to have the best effective nuclear charge because it's closest to the nucleus. It can feel the interaction of those protons pulling on it. So when you have hydrogen, you've got 1 proton and 1 electron. When you have helium, you have 2 protons and 2 electrons. And even though we're increasing electron for each proton, as we increase those protons, they far outweigh the extra electron repulsion that's added. So the first thing we see is that as we go across the periodic table, we start building up our protons, and therefore we start increasing from left to right our effective nuclear charge. And we're actually going to come to a pretty simplistic equation that talks about this in a few minutes. So that's the idea behind effective nuclear charge. So there's a phenomenon that we have to account for that's called shielding effects. And shielding effects are discussing when inner core electrons, so not valence electrons, but electrons that are already in completed inner core shells, are going to shield or block valence electrons from this proton interaction. So to give you an example of this, let's take a look at lithium and sodium and potassium here. Okay, so that's what you would have going down the periodic table. So if I take a look at lithium, I'm in the 2s shell. So first I'm going to draw my nucleus. And then after I have my nucleus, I'm going to go ahead and I'm going to add my 1s shell. And then I'm going to add my 2s shell. And so the electrons in this valence 2s shell are being shielded by the completed 1s shell. So what that's saying is the electrons that are found in the 2s shell, they can't experience quite as strong a pull as the electrons that were in the 1s shell. That 2s shell is a little bit weaker because the 1s shell is shielding it. Those 1s electrons are sort of hogging the protons in the nucleus and shielding anything further out from getting as strong an interaction. And so you can probably predict what's going to happen as we go down here. If I drop down to sodium, from lithium to sodium, I've now added a 2p shell. And in addition to filling that 2p shell, the sodium has an electron in the 3s shell. And so I've completely filled and shut off my 2 level. So 2s and 2p are filled. They're done. We've reached that point where neon is a noble gas, and then we start back over at the 3s. And now we don't just have the 1s shell that's creating this shielding effect, but we in addition have the 2s shell that's creating that valence effect. That shielding effect to the valence electrons. And so as you continue going on, you could see, we'll just write here, for potassium you're going to have the 4s. And when you have the 4s, you're going to have the 3s and the 3p. And you're going to have the 2s and the 2p, and you're going to have the 1s. So we're building up, we're getting further and further away from the nucleus, right? Now the nucleus kind of counteracts this, because as we go down the periodic table, we are adding more protons into that nucleus. And so that's something that's kind of important to consider. So when we get ready to examine how to actually calculate the effectiveness of the nuclear charge, we're going to use a simple method, and if you note here, I say the real method is a bit more complex, and I don't want to get into it. I'll mention it briefly here, but I don't want to get into it in great detail. But what we're going to do is we will use this equation here. So it's Z and subscript EFF, that's for effective, equals Z minus S. Now, when we look at Z here, Z is the atomic number. And if you think about what the atomic number is really talking about, it's talking about the number of protons that would be found in the nucleus of any given atom. So this is really the weighting or the addition of our protons into the nucleus. And if you can't guess, S is going to be for the shielding constant. And S has to do with the number of inner core electrons that have been closed off and are surrounding the nucleus, preventing the valence shell from feeling the effects. And so the difference between these two is what's called Z effective. And Z effective is our effective nuclear charge. Now this is a very simple method. It's not even algebra, it's basic arithmetic. Okay? So if we were to take a look here, let's take a look at, you know what, we'll do lithium and sodium to start again. So let's take a look at lithium. What is Z for lithium? Z would be 3. So if you go and you look on a periodic table, you would find that it is 3. It's element 3. Okay? Now what is S? It has 3 electrons total, but when we look at this, we're talking about just the core electrons. So we're in the 2s shell, so we're only interested in the number of electrons found in level 1. And in that case, we have 2. And so 3 minus 2 is plus 1. And so the effective nuclear charge for lithium would be plus 1. Okay? So the next one we're going to do is sodium. So let's take a look at sodium. Sodium is element 11, so that would be the Z. It's got 11 protons. And now we're in the 3s shell, so we have to go in and account for the core shell of 1 and the core shell of level 2. And in level 1 we have 2 electrons. But in level 2, how many do we have? We have 6 from the p shell, and we have 2 from the S shell, so that's a total of 8 in level 2, plus the 2 in level 1 is a total of 10. And 11 minus 10 is plus 1. So if you see what's going on here, okay, as I move down a row, what's happening? I'm maintaining the same effective nuclear charge. So what you see is that the nuclear charge for, or the effective nuclear charge for lithium and sodium, and if I worked out potassium, we would have the same thing, are all going to be plus 1. So what that really is telling us in terms of the trend is there's not a whole lot of fluctuation in effective nuclear charge as I go down a group. Now, that being said, it is true that the shielding effect, because we're adding more and more valence electrons as we pile them in, and then they get sealed off in an inner shell, and then our next valence ones come, we're building up those inner shells, and so we're further removing our valence electrons from the protons every time we move down the table. Now we add additional protons, which will help counteract that, but in reality, the shielding is going to start overshadowing the effective nuclear charge versus the number of protons that are being added. So in reality, we're going to start losing some of our effective nuclear charge as we move down the periodic table. For the purposes of general chemistry, it is acceptable to say there's not a significant change, or there's no change as we move down. Okay, I just wanted you to know in reality those shielding effects are going to come into play when we're dealing with the protons. There's weighted equations that get more complex. I don't want to talk about those right now. We're just going to deal with the simple as the effective. So I want to bring up one other thing here. Let's take a look at beryllium, and then let's take a look at boron. So beryllium, in case you didn't know, as I write this out here, beryllium is the neighbor to lithium, so Z would be equal to 4. And now, here's where we can find the trend moving across the table. If I take beryllium and I look at what S is still 2, just like it was for lithium. And that's because only the 1s shell, we're still in the 2 shell right now. We only have the 1s shell before us. So what ends up happening is I can add extra electrons into my valence shell, and they come with the benefit of an additional proton when I go across the table. Those additional protons bring a stronger pull for those electrons down into the center of the nucleus without having an increase in shielding effect. So if you look and you solve beryllium here, you're going to get a plus 2. And what do you think is going to happen for boron? Well, boron is element 5, so we're going to put Z equals 5 here. And again, we're still in the 2 shell. We're in the 2p shell now, but we're still in the 2 shell. And so we're going to put 5 minus 2, because that's the number of electrons in the 1. And then we are going to do that, and that equals plus 3. And so plus 3 would be the effective nuclear charge for boron. So look at what's happening to the effective nuclear charge as I move across the table. I'm looking, lithium plus 1, beryllium plus 2, boron plus 3. It's going to keep going and going up through the noble gases, which are going to have the highest effective nuclear charge, because they've got the largest number of protons in that row that you're, or that period that you're going across, and they're going to have therefore the tightest grip or binding of those electrons down into the nucleus, because they have a large number of protons and no change in the shielding effect. Now once we jump to the next level, when we go down, we're going to have to reset that shielding effect there. Okay, so that's really how we talk about or understand effective nuclear charge. So if we go to the next portion here, to sum up, effective nuclear charge is going to increase across a period. And the reason for that is that we're going to have an increased number of protons, and we're going to not have an increase in the shielding effect as we're going across. Okay? And then if you note here, it says effective nuclear charge does not change or slightly decreases going down a group. Okay? Either answer would be acceptable at this point. Based on the Z-effective equation we're using, we're saying that it does not change. It's fine to know in reality that the shielding effects would outweigh the additional protons, and so there would be potentially a slight decrease going down a group, but either of those answers are acceptable. So this is our first periodic trend. Effective nuclear charge is going to increase as we go across a period. That's the biggest thing that you want to take away from this. And as you go down, not much change, or it slightly decreases, but the effects are going to be pretty negligible. All right, so let's keep going. Atomic radius. So if we think about atomic radius, this is going to be a little bit quicker than effective nuclear charge, because now that we have effective nuclear charge in place, we are able to understand some of these other trends. So the atomic radius will increase as we go down a periodic table. And if you think about this, this makes sense, because that's due to an increase in the number of core electrons. So for instance, if I take lithium, I'm in the 2s shell. If I take sodium, I'm in the 3s shell. If I take potassium, I'm in the 4s shell. I'm building these shells. They're getting larger and larger and larger. And my core electrons, there's more and more and more core electrons that are filling up those inner shells and pushing the valence shells further out. So as I'm going down the periodic table, the additional shells are going to create a larger atomic radius. And that's pretty logical. I think that makes sense. But what about as we go across a period? Well, it so happens that as we go across a period, or we go across a row, the atomic radius is going to decrease as we go across that period, and that is due to the effective nuclear charge. And if you think about that for a minute, it makes sense. As I increase my effective nuclear charge, and we understand as we go across the table, we increase effective nuclear charge. We just discussed that, okay? As the effective nuclear charge increases, it pulls the electrons in tighter to the nucleus. So what you should do is imagine this giant sheet of electrons, right? And there's a strong center, the nucleus, that has these protons. And every single time that the effective nuclear charge increases, it pulls that sheet of electrons in just a little bit tighter. And so the radius shrinks down just a little bit, because that center, that proton source, is pulling in those electrons just a little bit tighter each time we go across the table for one element. Okay? So the atomic radius is going to decrease as we go across the period due to the effective nuclear charge. And so if you look at that, if we took something like, let's say, nitrogen, oxygen, and fluorine, well, nitrogen is going to be the largest out of them. Okay? Even though it's an element that's further back, it's smaller in atomic number, it has fewer electrons. What's happening is, as I go across, I'm increasing the effective nuclear charge. So oxygen has one additional proton compared to nitrogen, and it doesn't have a change in the screening. And then fluorine has 2 more than the nitrogen and 1 more than the oxygen with no additional screening effects. And so it's pulling in those electrons tighter and tighter. So again, atomic radius will increase going down the periodic table, more and more shells. And then the atomic radius will decrease as we go across a period due to the effective nuclear charge. So how about ionic radius? And this is important because when we deal with ions, the ions can form plus or minus charges, and that can affect the radius differently. So if you look here, cations are going to lose electrons and therefore increase the proton to electron ratio. So you lose an electron, which is the definition of the plus or the cation, you're going to increase the number of protons relative to your electrons. If you think about this, this is going to increase the effective nuclear charge, because what you're doing is you're removing an electron and you're increasing the number of protons compared to those electrons. That's going to pull those electrons in a little bit tighter, and that's going to shrink the radius because you're increasing the effective nuclear charge. Opposite if the anion is present. So for an anion, we're going to gain electrons. Those are your minus charges. You're going to decrease the proton to electron ratio. We're increasing those electrons, so the proton ratio falls down in comparison to the electron ratio. And therefore, that's going to decrease the effective nuclear charge, and that's going to enlarge the radius a little bit. So it's going to lose a little bit of that grip that it would normally have. So here's some practice. Why don't you go ahead and practice? List from decreasing to increasing the effective nuclear charge here. So we've got sulfur, aluminum, and magnesium, and we've got nitrogen, oxygen, and fluorine, and then it says here, list the following atoms in increasing radius size. Smallest first. Okay, so you want to get the smallest one first, and then you're going to go for the largest. So I will go ahead and let you guys do that, and then why don't you pause, and I'll put the answers up here in a minute. Okay, so here are the answers that you guys should have. And so hopefully these make sense to you. So if we look here, okay, so let's take a look at the first one. As we look at the first one here, you have sulfur, aluminum, and magnesium. Magnesium, okay, is going to have the weakest effective nuclear charge. And so when we're dealing with the going across the table, magnesium to aluminum, and then we're looking at sulfur, okay, we're going across the table, we're increasing the effective nuclear charge as we go across that table, because we're adding additional protons. However, the electrons are not increasing. The core electrons are not increasing, that's what I should say. And then for the next one, nitrogen, oxygen, and fluorine, that's already in the correct order. Nitrogen, oxygen, and fluorine. Because we're going, again, across the periodic table here, and so the effective nuclear charge is going to increase as we go across each of those. So decreasing to increasing order, those should be your answers. Now it says, list the following atoms in increasing radius size, smallest first. And so if we take a look at that, what we're going to find is that fluorine, chlorine, bromine, and iodine are already in the proper order. Because fluorine at the top is the smallest, we add more and more shells as we go to chlorine, as we go to bromine, as we go to iodine. We're increasing the number of shells that are found in the valence, or the outermost shell. And those core electrons are piling up. So therefore fluorine would be smallest, iodine would be largest. And then to wrap up with the final one here, we have the oxygen, the fluorine, the sodium, and the magnesium. The proper order for this would be the fluorine first, because it is the smallest one. And then the oxygen would come after that, okay? So remember, as we go across the table, we're decreasing in size. So the fluorine's first, then comes the oxygen, because that's one further back. And then if we backtrack, now we're going down one more level, but we're still backtracking. We have sodium and magnesium on the left side of the table and a shell down, so those are definitely going to be larger. Now the question is magnesium larger or is sodium larger? Magnesium is larger. Magnesium is smaller because it has a slightly better effective nuclear charge, and sodium would be the largest. Okay? So hopefully that makes sense to you guys. As always, thank you very much for watching.